Okay, so this set of lecture slides, we're going to be looking at a multipole expansion for the vector potential, for magnetic vector potential. So remember back a few chapters ago, we looked at the multipole expansion of the electric potential, and we found the monopole term, which was went as 1 over r, the dipole went as 1 over r squared, etc. We found this sum, the potential was equal to the sum of integrals, and this was for the multipole expansion of the potential of an arbitrary localized continuous charge distribution. The n equals 1 term we called the n equals 0 term we called the monopole term, n equals 1 was the dipole term, n equals 2 the quadrupole term. So we're going to try something similar now for the expansion of our vector potential. This time we want to find the magnetic vector potential at a point P in space outside an arbitrary localized current loop. So here's our loop of current I, here's our origin, and here's our point P. This is our separation vector R, and we know that at least in the Coulomb gauge, our magnetic vector potential is mu naught over 4 pi integral 1 over r j d tau. And we can write that in terms of the current I dl prime. So just like for our multipole expansion for the electric potential, we can make the replacement. We found that 1 over the separation vector r, we could write as 1 over r, the sum, n equals 0 to infinity, r prime over r n, times these Legendre polynomials of cosine theta prime. So I could go through the same steps, but you just go look back at our lecture slides of the multipole expansion of our electric potential to get how I got to this 1 over r expression. So I plug in what 1 over the separation vector is into the integral. And I do the sum, and I get these terms. So this is the multipole expansion of the vector potential of an arbitrary localized current loop. And so the integrals here I'm doing around the loop. The n equals 0 term is called the monopole term, n equals 1 dipole term, n equals 2 the quadrupole term. If we look now at the monopole term, this is just a line integral around a closed loop, so that's going to be 0. So the monopole term is 0. The dipole term here, if we want to take a little closer look at it, we can express our r prime cosine theta. So here's our r prime cosine theta prime as a dot product. R hat dot r prime is equal to r prime cosine theta prime, r hat being in the r direction. So I plug that in. Then we can rewrite this using this equivalency here, that the line integral of r hat dot r prime dl prime is equal to minus r hat crossed with the surface integral a prime. And you can see problem 161 in your textbook for the proof of this equivalency here. So I plug that in to my magnetic potential vector. And I just rearrange some things. And change the order of the cross product to get rid of that minus sign. And then I'm going to now define a new term, a new quantity called the dipole moment of the current loop that has symbol little m that I'm going to define as I integral dA prime. And if I plug that in, I get that the dipole term for our magnetic potential vectors mu naught over 4 pi, the magnetic dipole moment m crossed with r hat over r squared. So if you remember when we looked at the electric multipole expansion for the electric potential, we talked about the pure electric dipole as being equal to exactly the dipole term in the multipole expansion, which was this qd cosine theta over 4 pi epsilon naught r squared. And you'd have a configuration of charge such that its electric potential was exactly equal to the dipole term in the multipole expansion when the distance between the two charges in the dipole went to 0. But if the distance between the charges go to 0, then your potential goes to 0 unless you take your charge, the charges in the dipole, to go to infinity. So we found if D goes to 0 and Q goes to infinity, then your electric potential is exactly equal to the dipole term in the multipole expansion. Now we can look at the same thing, a pure magnetic dipole. This is when the vector potential, the vector potential of a pure magnetic dipole is exactly equal to the dipole term in the multipole expansion. This happens when the area of your current loop goes to 0. So make sure you remember this A here is area, not the magnetic potential A. But if your area goes to 0, then your magnetic potential goes to 0 unless your current goes to infinity. So the situation where the magnetic potential is exactly equal to the dipole term and the multipole expansion is when the area of the current loop goes to 0 and the current in the current loop goes to infinity. Now we can look at the magnetic field of a pure dipole. And we're going to be looking at spherical coordinates and also the magnetic dipole moment going in the z direction. So here this should say we're going to start with the magnetic potential of a pure dipole. Which is equal to mu naught over 4 pi m cross r over r squared. M cross r is going to be equal to m sine theta in the u phi direction. So to find the magnetic field of our dipole, you just have to take the curl of the magnetic potential. And remember, we're using spherical coordinates. So the curl looks like this in spherical coordinates. So here we only have a term u phi term So there's going to be a lot that cancels out. This has this is a phi, so we have an a phi term, so that stays non-zero. We don't have an a theta term, that goes to 0. We don't have an AR term, that goes to 0. This stays non-zero. A phi term goes to 0. AR term goes to 0. So this is what we're left with. Now I plug in what the a phi term was, mu naught over 4 pi m sine theta over r squared. And again over here, mu naught m sine theta over r squared over 4 pi. And then I have to do, this is just an integral in terms of theta. I take everything out except what depends on theta. So I have a sine theta squared. Here it's a derivative with respect to r, so I take out everything except for the 1 over r. The r's here, the r cancels out with one of the r squareds. I do the derivative, dd theta of sine theta squared, ddr of 1 over r. I cancel some things out, like the sine, thetas cancel out. We multiply the r's over here. I take out my common factor, and I get the magnetic field of a pure magnetic dipole. And this is what it's going to look like if I have the pure dipole with dipole moment. It should be dipole moment m along z. And this is what it would look like for a physical dipole. The magnetic field of a physical dipole with dipole moment m still pointing along z. Dipole moment of a magnetic field of a pure dipole, again with the dipole moment along the z-axis. So you'll do this problem, and that is it for these lecture slides.